All right, next up, Snake Eater 2. This was the first of what I like to call the sequels. So this is Snake Eater 2 as a sequel to Snake Eater 1. And so this was medium. I'd probably say this is like medium plus if that was even a difficulty level, but it's not. So let's get this one going. Snakey boy .7zip. All right, so we've got snakeeater2.exe. Again, it is a Pi installer file. We could tell that by the icon. So whereas Snake Eater 1 was about using procmon to identify file write to the file system, and then the flag was the name of the file, so all you had to do was identify the fact that the file was being written somewhere to the file system, and you got the flag. Snake Eater 2 kicks that up a notch. So let's approach Snake Eater 2 the same way that we approached Snake Eater 1. So in other words, let's break out procmon and study the malware dynamically to identify the file writes that it's doing to the operating system. So in procmon, as always, we're going to rely on our filters here so that the filter I used for Snake Eater 1 is actually still going to work here. So process name contains Snake Eater. So let's actually include that. And then we go ahead and we execute our Snake Eater 2 binary. And then if we then take the knowledge that we learned from Snake Eater 1 and we can actually add, let's do like path contains flag. So if you're thinking, oh, this is going to be just as easy as Snake Eater 1 because the flag's just going to be in there. So again, Snake Eater writes a flag somewhere randomly in app data. It actually writes a temp file first. It makes sure that it can write there. It deletes the temp file and then writes the flag. But whereas before the name of the flag was the actual flag in Snake Eater 1, this time we only have flag.txt. This flag is written to the operating system in a random directory. The flag contents are written into this file, and then the file is deleted immediately after that. So we don't have the flag, we just have where the flag was written. So in the code for Snake Eater 2, that is a 2-line change in writing Python, but it makes all the difference in how you actually approach this because it's a lot more complicated to dynamically retrieve the contents of a file that were written somewhere on the operating system and then deleted. It's a lot more involved to actually get the contents than it was to identify the metadata of the name of the file. So I saw a lot of approaches. Again, it was an absolute blast watching people try to figure this one out. I saw a lot of approaches that had to do with reverse engineering the static code of the file. This is another PyArmor PyInstaller app, so that was tough, but you could do it. I also saw people writing like PowerShell scripts to grab the contents of the flag as soon as it was written and then copy it to another directory. I saw people remove delete access to app data and the process so that the flag file was written but wasn't deleted, but then the temp files wouldn't be deleted, so it would just start spewing temp files all over the place. This one was so chaotic. It was so much fun. I'm going to show you again because, you know, I'm a busy guy. I got things to do. I'm going to show you the like super shortcut way to do this one. We're going to break out a tool called API Monitor. So the approach here is to identify file write to the operating system, but just getting the file itself isn't going to be enough. We actually have to get the underlying data that was written into the file, and we can do that through API calls. Now, if you're debugging this executable, if you're debugging the malware, you could eventually get to that, but that was a lot of work. And to step through this program manually until you could find the actual file write primitive was a lot of work. And API Monitor kind of does all of that heavy lifting for you. So I think API Monitor was like the easiest, the best approach here to identify this. So we're going to use API Monitor to hook and print out information about the API calls that this malware is making. And specifically, we're looking at the file IO primitives. And even more specifically than that, the APIs exist on a continuum. There are high-level API calls that expose like really easy, simple APIs to work with. And then there are low-level ones, which are like almost you have to write them in assembly, and they're doing syscalls to the actual kernel of the operating system. And so the way this binary was written was that it was performing a very low-level syscall to actually write the buffer of the flag bytes into the file. And so we're looking at very, very low-level file IO primitives here. So what we want to do, I believe it's going to be NT native. We can actually just check a bunch of these and you know, kind of pare it down a little bit. But like the NT native calls we want to look at, we probably want to throw in undocumented there just for good measure. I think NT native and undocumented is going to get us what we're looking for. So once you've checked those two as the actual APIs that you want to watch, you're going to monitor new process, and you're going to go over and find Snake Eater 2, and you're going to kick this off. And so it's going to do its thing. Remember, you could run this with a -v. In fact, I'm actually going to do that because it's funny. Snakeeater2.exe-v. And we've changed up our ASCII art, and we have a different lyric from Snake Eater from Metal Gear Solid 3. But we do the same thing. Here looks good, Smoke Bomb. So what we want to do is go find the APIs for that file write. So if we look around in the output of API Monitor, we're eventually going to find a couple of NT file primitives. So we've got like NT close, NT open file. To pare this down a little bit, we're going to locate this API in filter. If we locate API in filter, we get into the ntdll.dll file primitives. And so these are the low-level, like almost syscall level APIs for working in files. And one that we're really interested in is ntWrite file. So we can actually like uncheck everything else. If we hit this X and uncheck everything else, and then let me just go find that again, locate API and filter. Let's just sort on ntWrite file because that's the one that we actually care about. And let's monitor a new process again and rerun Snake Eater 2. And now, if we ignore the other instances of the running process, so we can actually even just remove these so we don't get confused, we've got our additional 2 processes here. And so we've got our 2 file writes at the NT level. We've got the first one that goes to the temp file, which only writes a single space, which is a hex character of 20. And then we got this one. And so among other things in here, we've got things like the file handle itself. So this is like the very low level primitives for how to handle files. But this one right here, pvoid buffer, this is the pointer to the buffer of the bytes that's written into the file. And if we look at the hex buffer before or after the call takes place, we see the bytes of the flag written into the file. So that was one of the ways to solve this challenge, was to load this up in API Monitor, look at the lowest possible level file write primitives, and that's going to be the ntWrite file primitives, and then look at the parameters that were captured by API Monitor and look for the buffer that was written into the file itself. And there is your flag. And that is Snake Eater 2. I saw a ton of awesome approaches to that one. If you've got another approach to how to solve that one, I'd love to hear it. So like leave a comment or like link your write-up or something like that. I'd love to read it. So there you go.